Section 6.5, circular functions. We're going to take different approaches looking at our trig values. We're going to look at them as if we were a point on a circle, and this circle, being the unit circle, is going to have a radius of 1. And as we spin this point around our circle, we create, with the exception of those 4 locations we've talked about before, triangles, right triangles. And that right triangle has some angle measured from the x-axis that we know is a reference angle, but it also has an angle of theta, which is measured from the right side, or the positive x-axis. And remember that our angles turn positive when they go counterclockwise, and they turn negative when they go clockwise. And we're going to set up our trig functions with regards to this x, y, and this r value of 1. So we should all be familiar with our ratios for our trig functions, and here we're specifically looking at sine and cosine. We know the sine theta is a y over r, but that r becomes a 1, and y over 1 just becomes y. So we can measure sine theta as being equal to just the y values of this point that's on our unit circle. And the same thing happens with cosine. So r becomes 1, x over 1. Cosine just measures the x of this point on our unit circle. So the concept that we need to get straight here is that with regards to this point that's moving along our unit circle, the distance in the y direction that that point is away from the origin, or the center of our circle, is what sine will measure. And the distance from the origin that that point is in the x direction is what cosine measures. So in defining the sine and the cosine functions and writing it for function notation y equal f of x, if f of x is equal to cosine of theta, what this y represents, the dependent variable, represents those horizontal movements, the horizontal position of the point. So it's measuring the x distance of the point. And then the sine, f of x equals sine of 0, where our y, our dependent variable now, is reflecting the vertical position, the y values of that point. So that's the stuff we need to get squared away. And it looks a little weird in this notation, because you'll notice the function notation, both of them use y equal cosine theta, y equals sine theta. But remember, what y represents for the cosine function is this x distance from the center of the circle. A little bit confusing there at the beginning. But once we start to look at the graphs, it's become a little clearer. So our angle, theta, remember, could be expressed in degrees or radians. We could be using variable x there as well. And so if we spin around our circle here, let's talk about the domain and the range of these sine and cosine functions. So our domain is dependent, our independent variable, is going to be this theta value. And we can turn positive angles, we can turn negative angles, doesn't matter. We will always get a value that we can use for our angle, and therefore the domains of sine and cosine functions, we'll just use theta right now, but could also be x, is all reals. An angle can be anything. So that would be our domain, x, such that x or theta, depending on what we're using, is equal to all reals. Now the range is a different story. And let's go back up to the unit circle to look at this. So as we move our point around this circle, you'll notice that in terms of the y values, that our circle maxes out at a 1, and then it has a minimum value at a negative 1. And it goes in between 1 and negative 1. And the range, being this y value that we're measuring This y value, again, could represent this x distance for cosine, but it could also measure the y value for sine. Even if it did the cosine distance, let's check that out. What are the largest values that you would get for y equal cosine theta? Well, you get a 1 as the largest value of x, and you would get a negative 1 as the smallest value. So it appears that the range for cosine and sine both have a value between 1 and negative 1. And we'll, again, once we graph these things, we'll take a look at that. So we'll say that our range, y is, I'll use some interval notation there, or you could write it as y such that y is less than or equal to 1, but greater than or equal to negative 1. And that's the range of our function, sine and cosine. So domain, theta, we can turn any angle, positive or negative. Our range values, though, this distance from the center comes between negative 1 and positive 1 for both sine and cosine. Again, getting a little preview of what's to come with the graphing. What happens to our x and y values? So thinking about our points spinning around the circle, what happens in these different quadrants? So let's focus on quadrant 1 for right now. And we're going to take our point and we're going to spin around the circle in that quadrant right there. And anytime I'm on that part of the circle, and again, I'm starting at 0 degrees and I'm going positive. So as I do this, if I start at 0 degrees and I go positive, I can see what's going on with my x values and my y values. Going from 0 degrees up to 90 degrees, we see that my points x values, they get smaller. Remember, they're starting at 1, 0, and look what they end up at, 0, 1. Because again, we're talking unit circle, radius of 1. So in that case, we can see that x's go from 1 to 0, which means they're decreasing, and y's go from 0 to 1, which means they're increasing. So x values are decreasing, and we can say from 1 to 0, and our y values are increasing. And that's happening from 0 to 1. So that's quadrant 1. What happens in quadrant 1? See what happens in quadrant 2. So now we're doing this, going this way, going from 90 degrees, which again is 0, 1, to 180 degrees, which is negative 1, 0 for a unit circle. And we can see x's are getting smaller still. They're going from 0 to negative 1, and y's are getting now smaller as well, from 1 to 0. So x values continue to decrease in quadrant 2. 0 to negative 1. And so do y values. This time from 1 to 0. And we just keep making our way around the circle. So quadrant 3 now. Now we're going here. Going from what would have been negative 1, 0 as a coordinate, to 0, negative 1. X values are now increasing. From negative 1 to 0. Y values continue to get smaller. This time, though, from 0 to negative 1. And then finally, quadrant 4 is going on this side. Going from 0, negative 1, back to 0, 1, 0. X values continue to increase as I move along that arc of the circle. This time increasing from 0 back to 1. and y values also increase. This time from -1 back to 0. So that's what's going on in all four quadrants for our sine and our cosine functions. And again, this will be helpful when we look at the graph. Periodic. So sine and cosine graphs are what we call periodic functions. And what makes something periodic is there is a repetitive pattern or a repetitive behavior with the graph. And so when we graph these things, they're going to look like a wave. I don't know if you guys have ever looked at like in an electronics class, you have something on the scope, and you see the scope with all these wavy lines on it. That would be periodic. Periodic behavior occurs in all kinds of different ways. We have periodic behavior in our music with our notes and the waves that those notes create. We have periodic behavior with light, intensity, tides. You can model as periodic behavior, high tide, low tide, something on a spring oscillating back and forth. So there are a lot of applications to using sine and cosines within a modeling situation. So we move our point continuing along this unit circle, and as we do that, we create these wave patterns, and again, we'll take a look at those in the next section. But here's just the different representation, our point spinning around from quadrant 1 to 2 to 3 to 4. And again, just remembering that theta is always coming from that 0. So these are what the thetas would look like in each of these respective quadrants. All right, so let's just arbitrarily pick some point. We'll go ahead and stick with the point that's represented here, quadrant 1. Some point x, y. And there are multiple situations that would produce that same coordinate value at that point. One of them being, all right, sine of the theta. So we're just going from 0 up to the terminal ray of that angle. And if we did the sine of that, we would get this ratio of y to r. But what if we've gone around the circle again in such a way that we started where we left off and we traveled around the circle in a full rotation and ended up right back to where we started from? Well, anytime we travel around the circle, we're talking in radians, a distance of 2 pi. Or if we're talking degrees, 360. So we can represent multiple solutions to this, meaning we can have different angles that produce the same xy value if every time for sine and cosine we always rotate another full circle, or 2 pi radians, takes us back to that same location. And so that's what this notation means, this theta plus 2k pi thing. That just means I start at the original angle and I add another rotation. And this k value that's in here can just represent the number of rotations we are making. It's an integer value, so we're not going to write that as fraction or decimal. I could have 4 times around, which means my k would be 4, and then this whole process would be 2 times 4 times pi, or 8 pi would represent 4 rotations. And so all this notation just simply means is multiple revolutions. It's theta plus 2k pi. And that's the case with sine and cosines. With tangents, it's different because they have certain values. Their values we can get back to the same answer, same solution-wise, with just the rotation of pi sometimes. All right, so just introducing you to some notation that you might see, this whole theta plus 2k pi thing. So let's see how that applies here in this first example. If we have some cosine of some angle producing a 0.7893 ratio, what is the value of each of the following? So we're using this as our ratio. Again, that's our x to r ratio right there. And let's see, picture-wise, where would this cosine of 0.7893 be? In a real quick sketch, 0.7893, maybe right there. There's my little diagram where we can call, there's my unit radius length of 1, and then my x value would be this 0.7893. There's my x to r ratio for cosine. So we have some y value that we don't know. We can find it, but we don't need it right now. So we're going to take that point, and we're going to start at that exact angle x that we've rotated already. And we're going to add to it a 2 pi rotation. So now we're going to go around and get back to the same spot. So let's say if we did that, we'd have cosine of x, which we know is 0.7893. But we're taking that value of theta, or x in this case, and we're adding a 2 pi rotation. So we have now x plus 2 pi. And what would we get there? Well, if I end back up at the same exact spot, that must mean I have the same exact ratio, 0.7893. All right, to illustrate this a little further, let's actually figure out what would have been, for this example here, what would have been the angle that produced that ratio? Well, if we did the inverse cosine in radians of 0.7893, that would tell us what this angle is. And it came out to 0.661 radians. There's my angle. And then now what we can do is add 2 pi to it. So x plus 2 pi would mean 0.66 plus 3.14. And we have 3.801 radians. So now let's just see what would happen if we took the cosine of 3.801. So we put that, and we get, oops, silly me. We don't want to add 3.14, that's not a full rotation. We want to add 2 pi, or 6.28. All right. So we're going to get 6.941. So now let's take the cosine of 6.941, and we should end up with that. See what happens? Take the cosine of that value, and yep. Now we get a little difference in our number because I've been rounding, but yeah, we should be back to the same place. So you got to just watch the rounding. So that's what's happening. Take our radian angle that we have, we add to that radian 6.28, which is a full rotation, and we get back to the same location on our circle, which means we have to end up with the same value ratio-wise. And in each of these examples, you'll notice that my 36 pi, remember this is the 2k pi part of my problem, and this negative 22 pi is the 2k pi part of my problem. So in each of these, we can figure out this k value, which is talking about my number of rotations. So divide by 2 pi, and we discover that k means we've gone around 18 rotations. On D, we divide by 2 pi, and we discover that k has gone around 11 rotations in a negative direction. And that's the case up here too. We just go as a negative rotation back to the same point. So back on our unit circle example, now we're just going this way and getting back to the same spot. So each of these values, B, C, and D, because we've gone around multiple revolutions, give me the same values, 0.7893. Okay, so there's our multiple revolution notation, that 2 pi k. Sines, cosines, tangents, without a calculator. So we're using right triangle information for these, most likely, or in some cases we might be lying on a quadrantal angle. So this would be a good time to review or refresh your right triangle notation. 1, root 2, and then we have our 30, 60, 90 triangle. 1, root 3, 2. And remember, those can all be in radians as well. So pi over 6 for 30 degrees, and pi over 3 for 60, and pi over 2 for 90, and pi over 4 for 45 degrees. All right, so what we do on these, we have been given some angle, and we are looking for these ratios. So I'm looking for what the ratio of this cosine of 4 pi over 3 is. So what we do first is, like we've done in the past with our other sections that dealt with this, we put ourselves in the right place. And the rotation of 4 pi over 3's, so a little review again, from here to pi, if I cut it into 3 equal parts, there's the first third, there's the second third, and of course this would be the third third. Each of those parts would be a pi over 3. And then another pi over 3 would make 2 pi over 3's, and then this would be 3 pi over 3's. So we're at 4 pi over 3's, which means I add another pi over 3, and now I'm right here in quadrant 3. So I'm looking for the ratio that produces that angle theta. We create our triangle from there. So I go back to the x-axis. Here's the triangle I'm interested in. It's a right triangle at the x-axis. What was this reference angle that we produced right there? Well, we've gone from a 3 pi over 3 to a 4 pi over 3 by adding a 1 pi over 3. So that is my reference angle. What do I do with that? Well, a pi over 3, that's a 60 degree. So I'm looking at that angle right there. There's my triangle. And I'm talking about the cosine of this, which would make our x become a negative 1. So this part of my triangle becomes a negative 1. This part becomes a negative root 3. And that part of my triangle becomes a 2. All because I've got this 60 degree reference angle right there. Across from the 60 is the root 3. The reason the root 3 is negative and the x is negative is because I'm on quadrant 3 side where x's are negative and y's are negative. So a cosine of that would be a negative value of x, negative 1, and an r value of 2. So a cosine of 4 pi over 3 is a negative 1/2. All right, let's go try this with our sine So I'm splitting into 6 now, 0 to pi, which is 6 pi over 6s. And to go to a 7 pi over 6, I've had to add another pi over 6. So there's my reference angle of pi over 6. And remember, the other way you can find this is if we know what our theta is. We had a rule down in quadrant 3 that said if I wanted to find my reference angle, I would do theta minus 180 degrees. But we're in radians, so theta minus pi. 7 pi over 6 is theta. 6 pi over 6 is my value of pi, which gives me a reference angle of pi over 6. All right, so there's where I am at a pi over 6. I know that on a pi over 6 triangle, the negative, because I'm down in quadrant 3, my 1 is across from pi over 6. My x value in this case would be a negative root 3. And of course, my hypotenuse is still 2. And so the sign of a negative, oh, didn't even see that. We went negative rotation. All right. Still would have the same reference angle, but, okay, let's clean this up. Same reference angle, pi over 6, but I went negative rotation. So I went this way. So my triangle is actually going to be over here. There's my alpha. That's still a negative 3. That's now a positive 1, and this is a 2. Okay. Wasn't paying attention. Sorry about that. So yeah, we went this way at a negative 7 pi over 6 rotation, putting us into quadrant 2. Signs are going to be positive there. So I have sine value, which is a y over an r, also equal to a 1/2. So the cosine of a 60 and the sine of a 30 are co-function relationships. They're going to produce the same values, reference angle wise. Right, and then tangent, let's go see what's going on here with tangent. Again, putting ourselves in the correct spot. So a pi over 2 puts us right there on the y-axis. So there's our angle that we turned. And at that point, we don't have a triangle. We do have this for a unit circle. We do know that that coordinate is going to be a 0, 1. And therefore, if tangents have a ratio of y over x, and my y is a 1, and my x is a 0, then I know that the tangent of pi over 2 is going to have to be undefined. All right, so some work without calculators. Definitely we'll be having to do that. Then we get into our basic identities. Reciprocal relationships, we've already seen them. I'm going to need to know all of these. So I would say flashcards or a formula sheet that you're studying regularly. Get it memorized so you know what you're doing with these. So we have reciprocal relationships. Remember the 1/overs. We also have what we call odd-even identities. And what happens here is you'll notice that my angle rotation is a negative rotation. So in the sketch, we're going this way. And this is where we go back to, we introduce these things and then we say, is that all? I don't use them anymore? No, we use them all the time. So ASTC, I'll support the covers. We need this to answer the questions here for these odd-even identities. What if you did a negative rotation? Well, that puts you down in a quadrant where cosine and secant are positive. Everything else is negative. And so that's what's happening here. A negative angle produced a negative cosine or sine value. negative angle produced a negative cosecant value. Going over to the tangents, that negative rotation put me where negative tangent occurs, and it put me where negative cotangent occurs. But you'll notice for sine or cosine and secant, that negative rotation put me in a place where cosine is positive. So that's why these two functions don't have the negative values in front of cosine theta or secant theta, because a negative angle just puts me in a place where they are already positive. So that's our even-odd relationships. Then we get into cofunction relationships. We just talked about this. We just had an example where the sine of a 30-degree angle, which produces a ratio of 1/2, is the same thing as a cosine of a 60-degree angle, which also produces a 1/2. And the reason that that's happening, you'll notice those two angles add up to 90 degrees. The other way of expressing sine of 30 is to say it's the same thing as sine of 90 minus the angle that we took over there with the cosine. So if we call this angle 60, just our generic theta angle, then this would become sine of 90 minus theta. And that is our cofunction relationship for sines and cosines. What's happened is, for a sine of an angle, the opposite side becomes the adjacent side of the cosine of 90 minus theta. So an opposite and an adjacent become each other depending on which of the two acute angles you're hanging out at. And that's what establishes these 6 relationships here called cofunction relationships. And lastly, the big one, it's called the Pythagorean identity. There are many identities that we can develop from this one, but we're just going to introduce the generic identity first. Here's how we create this thing. Going back to our concept of the unit circle. Sine is equal to y over r. Cosine is equal to x over r. Well, what if we wanted to solve each of these trig values for their respective variables? Well, if I did that, if I took sine of theta equaling y over r and I solved it for y, I just have to multiply r to the sine. And that's the same thing's happening with the cosine. So we're just taking these r values, which in our unit circle is a 1, but we're taking them generically as r, and we get these y equal r sine theta and x equal r cosine theta. And so then what happens in our right triangle up there, in our unit circle, is these x values become cosine theta times r's, and these y values become sine theta times r's. X squared plus y squared, r squared, that's just our Pythagorean theorem there. Legs squared equal the sum of the legs squared equals the hypotenuse squared. All right, we further develop this. We take r cosine squared, and we notice that the r has to be squared, the cosine has to be squared, the r has to be squared, the sine has to be squared, and we get this line. And then from there we can see that both of those functions have a GCF of r squared, so we pull that out in front, left with an r squared times a cosine squared plus a sine squared. Then we take that line and divide out our r squareds, and we get our Pythagorean identity. Cosine squared plus sine squared equals 1. And again, this is the derive from this one identity these other 10 that you see here. So I'll kind of real quickly give you the lowdown on how we get these. For us to go from the generic Pythagorean identity to these two, it's a simple maneuvering of moving cosine squared to the same side as 1 and sine squared to the same side. So 1 minus cosine squared gives me just sine squared by itself. And 1 minus sine squared just gives me cosine squared by itself. What happens over in this group? Well, initially what happened is we took this function to get this one, we divided everything by a cosine squared. Divided the whole thing by cosine squared. So cosine squared over cosine squared became 1. And sine squared over cosine squared became tangent squared. And 1 over cosine squared became a secant squared. And then from that, all we simply did is we moved things around. So let's say we subtract 1 to the other side. We get tan squared equals secant squared minus 1. What if we subtract secant squared to the left and move the 1 to the other side? Then we get tan squared minus secant squared equals negative 1. What if we do secant squared minus tan squared? Then we get 1. In developing this other column over here, how we did that is instead of dividing by cosine squared, we divided now by sine squared. So cosine squared divided by sine squared is where the cotangent comes from. Sine divided by sine, 1. 1 divided by sine, cosecant squared. So that's where these came from. And again, same manipulation. So just be aware that you can take our generic Pythagorean identity, cosine squared plus sine squared equals 1, and develop these other ones from it. So I would suggest maybe trying that out on your own. See if you can come up with these 10, because they would be helpful for you to know so that we can do this stuff, which is simplifying using our identities. Now, it does get more complicated than this, but we're going to go pretty basic with our stuff for right now. So what we want to do when we simplify these identities or these expressions is we want to rewrite them. Sometimes maybe they'll end up as an integer, sometimes just another trig function value. And that's our goal. We want to make them look like one of those two things. And so what we look for is these relationships, these reciprocal relationships, or these Pythagorean identity relationships. And in this first example, what I have here, and it might be a good idea when you're doing these simplifying problems, is to maybe at least put the Pythagorean identity up here. And then I'm also going to introduce you to two reciprocal relationships that we may not think about. And that's our how we can change the way we write tangents and cotangents. So if a tangent is a ratio of y over x, and we had established at the beginning of this that our sine is equal to y, and our cosine is equal to x, then I can say that a tangent is also equivalent to a sine theta over a cosine theta. So that's another relationship you might want to think about in regards to tangents. And then, related to that, it's reciprocal function, cotangent. Cotangent just does the reciprocal of tangent, which means a cotangent could be expressed as a cosine theta over a sine theta. So maybe we hang on to those, we look at those as we're working these problems out. All right, our first one, A, 1 plus sine squared plus cosine squared. Well, right off the bat, I see a sine squared plus a cosine squared, which I know is equal to 1. So this problem now becomes 1 plus 1 over a cosecant of x, simplified as 2 cosecant of x. We'll want to write this as a reciprocal, so we remember that 1 over a cosecant is the same thing as a sine of x. So we have some negative angles in here. So these are those even odd identities. A sine of a negative x. All right, we said that a sine of a negative x produces a negative sine x value. And a cosine of a negative x, a negative angle rotation, put us at a place where cosines were positive. Okay, going back to these relationships with odds and evens involved. All right, and if that's the case, if I have negative sine x over cosine x, well, we know that a sine x over cosine x is a tangent, so this must be equivalent to a negative tan of x. All right, and then our last one here. Sine, secants, cotangents. Notice we don't have any squared parts in this, so we're not thinking about a Pythagorean identity. But what I do want to do is change all of these to sine and cosine. Sine theta already has a sine, so I leave it alone. A secant of theta, though, is a 1 over a cosine. And a cotangent of theta is a cosine over a sine. Now, common terms here in the numerators and the denominators, sine thetas cancel, cosines cancel, and I just get an answer of 1. So that one is simplified just 1. There are more for you to try on the